Greetings and welcome to Lecture 6.7, Proportions. So we're going to discuss a proportion which is two equal ratios. That is, if A over B and C over D are ratios, then A over B equals C over D is a proportion. Now each of our numbers in our proportion is called a term, and they have labels for each of those numbers. So the first term is A, the second term is B, the third term is C, and the fourth term is D. And they even have more labels than that. So if you think about the first and fourth terms are called the extremes. The second and third terms are called the means. So the diagonals have names. So the downward diagonal are the extremes, the upward diagonal are the means. Here's why that's really important, because we have a property that says the product of the extremes equals the product of the means if this is indeed a proportion. So specifically, the property is the means and extreme property. If A, B, C, and D are all real numbers, but with B and D not equaling 0, then if A over B equals C over D, then we know that AD, the multiplication, the product of AD equals the product of BC. So the product of the extremes equals the products of the means. Let's take the example to solve the proportion for x where 3 over x equals 6 over 7. So using our extreme mean property or mean extreme property, my extremes are 3 and 7. My mean is x and 6, or 6 and x. So I'm going to take the product of the extremes, 3 times 7, the product of the means, 6 times x. Now I have 21 equals 6x. Divide each side by 6 to solve for x. X equals 7 halves. Let's try another problem. Let's solve for x in the situation where x plus 1 all over 2 equals 3 over x. Now it's very important that we do keep in mind that if our value that we come up with x is 0, then it's not a valid solution for this problem. Mathematically it would be correct, but for this problem it would not be a valid solution. So let's set it up. Our extremes are x plus 1 and x. Our means are 2 and 3. We're going to multiply the extremes, multiply the means, set them equal to each other. X times x plus 1 equals 2 times 3, giving me x squared plus x equals 6. Let's move the 6 to the side, to the left-hand side, so we can set it equal to 0. So I have x squared plus x minus 6 equals 0. We're going to factor that into x plus 3 and x minus 2. Now I'm going to use my zero factor property to solve for x. So x plus 3 equals 0, giving me x equals negative 3. X minus 2 equals 0, x equals 2. Now neither one of those equals 0, so they're both valid solutions for this problem. Now here's a problem I'd like you to solve, and then turn in at our next class session for credit. So solve for x. X plus 1 over 6 equals 7 over x. Now let me work through a problem. A manufacturer knows that during a production run, 8 out of every 100 parts produced by a certain machine will be defective. If the machine produces 1,450 parts, how many can we expect to be defective? So I need to set this up as a proportion to be able to solve it. So I do know the defective parts are going to be my numerator. The total parts going to be the denominator. At least that's how I'm going to set it up. So 8 out of 10 is going to be 8 defective parts out of the total of 100 parts. The defective, I don't know, out of 1450 is going to be x out of 1450, so x over 1450. Now since they're a proportion, I'm going to set these two fractions equal to each other, two ratios equal each other. So 8 over 100 equals x over 1450. We're going to use our means and our extremes to solve this. So our extremes are 8 and 1450. Our means are x and 100. Let's multiply our extremes, 8 times 1450. Multiply our means, 100 times x, giving us 11,600 equals 100x. Divide by 100 for each. So I get 116. X equals 116, which means that out of a run of 1450 parts, I can expect that 116 are going to be defective. To me, that's a lot of parts that are defective, and I'm going to have to throw away at a big expense, more than likely. So it might be time to change out machines. Let's try another example. A woman drives her car 270 miles in 6 hours. If she continues at the same rate, how far will she travel in 10 hours? Right. So I'm going to set it up in miles over hours. So she traveled 270 miles in 6 hours. We want to know how many miles will she travel in 10 hours. So I'm going to multiply my extremes, multiply my means, giving me 10 times 270 equals 6 times x. 2,700 equals 6x. Divide each side by 6, giving us 450x equals x. So in 10 hours, she will travel 450 miles. Let's work through another problem. A baseball player gets 8 hits in his first 18 games of the season. If he continues at the same rate, how many hits will he get in 45 games? How I'm going to set this up is hits over games. Now, it really doesn't matter if you do it the opposite way around. It doesn't matter. It's just you do want the hits over the game or the game over the hits. So I'm going to do it hits over game. So 8 hits in the first 18 games. I want to know how many hits he'll get in 45 games. Again, my extremes are 8 and 45. I'm going to multiply those together. My means are 18 and x. I'm going to multiply those together. So 8 times 45 equals 18x. 360 equals 18x. Divide by 18 for both sides, leaving me with x equals 20. So we can expect in 45 games he should have 20 hits. Right? That seems pretty reasonable. So that's it for this video. So until next time, be seeing you.